St. Joseph College for Women Autonomous, Visakhapatnam. Welcome to St. Joseph's open web based learning platform. So you learn for a soulful and enriching e-learning experience. Myself, Dr. G. Kumar, Assistant Professor, Department of Physics, St. Joseph College for Women, Visakhapatnam. First BSc, second semester Physics, Unit 5. Topic name is Special Theory of Relativity. Content of this topic is first one relativity and the special theory of relativity, second one frames of references and types, third one Galilean transformation, and fourth one Michelson-Morley experiment and a negative result, postulates of special theory of relativity, large transformation, time dilation, length contraction, Einstein's mass energy relation. What is relativity? The relativity deals with an object or a system which are speeding up or speeding down with respect to one another. Or sometimes the theory which deals the motion and the rest is also called theory of relativity. For example, if we compare a hockey ball with an atom, then it is extremely big, and if we compare it with the earth, it is extremely small. Thus we can say that size is relative. What is the special theory of relativity? It deals with objects and systems which are either moving at a constant speed of light with respect to one another or at rest. A rigid body. If you are applying any force on a body, the body does not undergo any change in shape or size. So such a type of body is called rigid body. Next one, coordinate system. Coordinate system is a system of measurement of distance and direction with respect to rigid bodies. Frame of reference. The motion of the body has no meaning unless it is described with respect to well-defined coordinate system. So the coordinate system is known as a frame of reference. For example, car is moving on the road, rocket or plane motion in the sky. The frame of references are two types. First one is the inertial frame and second one is the non-inertial frame. Inertial frames. When the bodies in this frame obeys all Newton laws. For example, a body not acted upon by an external force, it is at rest or moves with constant velocity. So such a type of frames are called inertial frames. Non-inertial frames. When the bodies in this frame, they not obey the Newton laws of inertia and other laws. For example, merry-go-round. Note, non-inertial frames are also belongs to classical mechanics because quantum mechanics interpreting the behavior of elementary particles and atoms. In inertial frames, let us consider a coordinate system to which a body in motion has coordinates x, y, z as the body not acted upon by an external force. According to Newton's second law of motion, F is equal to ma. So this can be written like this: m into d square x by dt square is equal to 0. And with respect to y axis, m d square y by dt square is equal to 0. With respect to z, m d square z by dt square is equal to 0. So if you are taking mass is a constant of the body in three coordinates, so d square x by dt square is equal to 0, d square y by dt square is equal to 0, d square z by dt square is equal to 0. So here this can be written like this: dx by dt is equal to ux, dy by dt is equal to uy, dz by dt is equal to uz, which gives here ux, uy and uz are the components of the velocities along x, y, and z axis, which are constant. Next topic is Galilean transformation. So Galilean transformations are used to transform the coordinates of position and time from one inertial frame to another inertial frame. So this can be represented in graphs. Suppose we have two frames of references named as S and S dash. Let the velocity of S dash frame relative to S frame be V. Consider an event happening at P with respect to S is x comma y comma z comma t, and with respect to S dash frame x dash comma y dash comma z dash and t dash. Let us consider our axes are x and x dash are parallel to V. Let y dash and z dash be parallel to y and z axis respectively. Also count the time from the instant at which the origins O and O dash coincide. We know the kinematic equations. V is equal to U plus AT. By using the above equation, we can write x is equal to x dash plus Vt, or x dash is equal to x minus Vt. So there is no relative motion along y and z axis. We have y dash and is equal to y, z dash is equal to z. Time is independent in space coordinates, so that's why we can write t dash is equal to t. So here the event is done in x-axis, that's why we are getting these four equations. X dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, t dash is equal to t. So that is equation 1. These equations are called as Gaussian transformation equation. The inverse Gaussian transformation equations can be expressed as x is equal to x dash plus vt, y is equal to y dash, z is equal to z dash, t is equal to t dash. That is equation 2. So Gaussian transformation and the inverse Gaussian transformation both are in opposite direction. That's why we are getting these type of equations. According to Gaussian transformation, some quantities like velocity are changed, while some quantities like mass, length, time, acceleration, etc. are not changed. The quantities or the laws that do not change under a transformation are called invariants. Invariance of conservation of momentum. Consider the collision of two particles according to the law of conservation of momentum. When no external force is acting, the total momentum of the system remains conserved. So this can be written like this: P1 plus P2 before is equal to P1 plus P2 after. Let M1 and M2 be the masses of the two particles. In frame S, let U1 and U2 be the velocities before collision, and V1 and V2 be the after collision velocities respectively. M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. That is equation 1. So same type of collisions occurred in another frame like S dash frame, which is moving with velocity v with respect to S frame. Then according to Gaussian transformation, u1 dash is equal to u1 minus v, u2 dash is equal to u2 minus v, v1 dash is equal to v1 minus v, v2 dash is equal to v2 minus v. It is equation 2, where u1 dash, u2 dash, v1 dash, v2 dash are the velocities before and after collisions in S dash frame. Substituting the values from equation 2 in equation 1, we get m1 u1 dash plus m2 u2 dash is equal to m1 v1 dash plus m2 v2 dash. That is equation 3. Equation 3 represents the law of conservation of momentum as observed in moving frame S dash. This shows that the law of conservation of momentum remains invariant under the Gaussian transformation. Next one is absolute frame of reference. In this, the velocity of light will have different values for different observers moving with different uniform velocities. Further, it was thought by the scientist that there must exist a preferred inertial frame known as absolute frame of reference in which the velocity of light will be exactly equal to 3 into 10 to the power of 8 meter per second and will be same in all directions as the frame is at absolute rest. Next topic is Michelson-Morley experiment. In this experiment, Michelson and Morley are the two different scientists had performed this experiment to verify the absolute frame of reference with the acceptance of the wave theory of light. It was thought that the space is filled with a substance called as ether. What is ether medium? It is a medium which is invisible, massless, perfectly transparent, perfectly non-resistive, having high elasticity and low density. So such a type of medium is called ether medium. So experimental arrangement. Light from a monochromatic extended source S after being rendered parallel by a collimating convex lens L fall on the semi-silvered glass plate G inclined at an angle 45 degrees to the beam. So it is shown in the figure. The experimental part is divided into two parts. One being reflected from the semi-silvered surface G, giving rise to ray 1 which travels towards the mirror M1, and the other being transmitted giving rise to ray 2 which travels towards mirror M2. The two rays fall normally on mirror M1 and mirror M2 respectively and are reflected back along the original paths. The reflected rays again meet at the semi-silvered surface of the glass plate and enter the telescope where interference pattern is obtained. If the apparatus is at rest in ether medium, the two reflected rays would take equal time to return the glass plate G. But actually, the whole apparatus is moving along with the earth. Let us suppose that the direction of the motion of the earth is in the direction of the motion of inertial beam. Due to the motion of the earth, the optical path transferred by both the rays are not the same. The reflections at the mirror M1 and M2 do not take place at A and B, but A and B respectively as shown in the figure. Thus, the time taken by the two rays to travel to the mirrors and back to G will be different in this case. Theory: let the two mirrors M1 and M2 be at an equal distance L from the glass plate G. Further, let C and B be the velocities of light and apparatus respectively. It is obvious from the figure that the reflected ray 1 from the glass plate G strikes the mirror M1 at A1 and not at A due to the motion of the earth. The total path of the ray from G to A dash and back will be G, A dash, G dash from triangle G A dash D by using the Pythagoras theorem. So we can write this equation: G A dash whole square is equal to A dash whole square plus A dash D whole square. That is equation 1. If T be the time taken by the ray to move from G to A dash, then from equation we have Ct square is equal to Yt square plus L square. So here we are changing the equation T square into C square minus V square is equal to L square. So T can be written like this: T is equal to L by root over C square minus V square. Let if T1 be the time taken by the ray to travel the whole path from G to A dash and next G dash to A dash. So this can be written like this: T1 is equal to T plus T, that is 2T, that is equal to 2L by root over C square minus V. T1 is equal to 2L by, we are taking C as a common, so 1 minus V square by C square whole to the power of 1 by 2. So T1 is equal to 2L by C into 1 plus V square by 2C square. So this can be written by using the binomial expansion theorem. Now consider the case of the transmitted ray 2, which is moving longitudinally towards mirror M2. It has a velocity c minus v relative to the operators when it is moving from G to P. During its return journey, its velocity relative to the operators is c plus v. If T2 be the total time taken by the longitudinal ray to reach G dash, then T2 is equal to L by C minus V plus C plus V. So T2 is equal to L into C plus V plus L into C minus V by C square minus V square. After solving the above equation by using the binomial expansion, T2 is equal to 2L by C into 1 plus V square by C square, that is equation 3. Thus the difference in time of intervals of the longitudinal and the transverse journey, delta T is equal to T2 minus T1. Delta T is equal to, substitute the T2 value and T1 values from the above equations. So we are getting delta T is equal to 2L by C into V square by 2C square, that is equal to L V square by C cube, that is equation 4. Therefore, the optical path difference between two rays is given by optical path difference is equal to velocity into delta T, that is equal to C into L V square by C cube, that is equal to L V square by C square. If lambda is the wavelength of the light, then path difference in terms of wavelength is equal to L V square by lambda C square. Michelson Morley performed the experiment in two steps. Firstly, by the setting shown in the figure, and the second by turning the whole apparatus through 90 degrees. The positions of the two mirrors are changed. Now the path difference is in opposite direction. That is, the path difference is equal to minus LV square by lambda C square. The resultant path difference becomes LV square by lambda C square minus of LV square by lambda C square, that is equal to LV square by lambda C square. The total optical path difference is 2LV square by lambda C square. So we know that a change in optical path difference by lambda corresponds to a shift of one fringe, and hence the path difference corresponds to a fringe shift 2LV square by lambda C square. Following were the data of the Michelson-Morley experiment. After substituting the values, L is equal to 1.0 into 10 to the power of 10 cube centimeter, lambda is equal to 5 into 10 to the power of minus 5 centimeter, V is equal to 3 into 10 to the power of 6 centimeter per second, and then C is equal to 3 into 10 to the power of 10 centimeter per second. Change in fringe shift N is equal to 2LV square by lambda C square. After substituting the values, we are getting the final value N is equal to 0.4 fringe. Thus, a shift of less than half a fringe was only expected. Michelson-Morley could observe a shift of about 0.01 of fringe. Of course, this shift is within the limits of the error of the observations. They repeated the experiment at different points on the Earth's surface and at different seasons of the year, but they could not detect any measurable shift. So, it was a null or a negative result. The negative result suggests that it is impossible to measure the speed of the Earth relative to ether, or the concept of a fixed frame of reference cannot be checked by experiment. In this way, the null result of experiment lead to the total rejection of the ether hypothesis. This suggests that the speed of light in vacuum is the same in all frames of reference, which are in uniform relative motion. explanation of relative negative result. The following explanations were given to explain the negative result of Michelson-Morley experiment. First one, ether drag theory. According to this theory, the moving earth completely drags the ether with it. It means that there is no motion in between earth and ether, that is V is equal to 0. So for that, T1 is equal to 2L by C into 1 plus 0, that is equal to 2L by C. T2 is equal to 2L by C into 1 plus 0, that is equal to 2L by C. Hence, there is no shift in fringes and the null result is explained. The above explanation was not accepted due to the following reasons. It is contrary to the experimentally observed phenomenon of aberration of light from the stars. Fringe has experimentally shown that a moving body could drag the light waves only partially. The partial dragging of light waves was also explained by electromagnetic theory without introducing the ether drag hypothesis. Fresnel-Lorentz contraction hypothesis is also explained the Michelson-Morley experiment's negative result. According to this hypothesis, all the materials bodies moving with a velocity v are contracted in the direction of motion by a factor root over 1 minus v square by c square. Hence, if L0 is the length of the body at rest relative to the ether and L is the length when it is in motion with a velocity v related to ether, then L is equal to L0 by root over 1 minus v square by c square. We have T2 is equal to 2L by root c into 1 minus v square by c square into 1 plus v square by c square. After that, we are getting equation 2L by c into 1 plus v square by c square minus v square by 2c square minus b power 4 by 2c power 4. Neglecting the higher order terms like v power 4 by 2c power 4, we get T2 is equal to 2L by c into 1 plus 2v square by 2c square minus v square by 2c square. So we get 2L by c into 1 plus v square by 2c square. So it represents equation T1. So hence T2 is equal to T1. Therefore, there will be no shift in the fringes. In this way, the negative result is explained. As this explanation is purely ad hoc, this was not accepted. Moreover, when the arms of the interferometer are not equal, this hypothesis fails to explain the result. At last, light hypothesis. According to this hypothesis, the light from a moving source has a velocity which is a vector sum of its natural velocity and the velocity of the source. Thus, the light from the source had always the same constant velocity relative to the interferometer. In this way, the negative result could be explained on this basis of certain astronomical evidence. This hypothesis was also rejected. Postulates of the special theory of relativity. Einstein proposed a special theory of relativity in 1905. He proposed two postulates. First one, all physical laws are the same in all frames of references which are moving with constant velocity relative to each other. According to this postulate, there is no absolute motion. This postulate is also called as law of equivalence. And the second one, the speed of light in vacuum is the same in every inertial frames. According to this postulate, the speed of light is the same in all directions with uniform velocities. This postulate is also called as law of consistency. The second postulate expresses the result of Michelson-Morley experiment. Next topic, Lorentz transformation of space and time. In this, the invariance of speed of light and the law of mechanics in all inertial frames do not hold and need to be modified without any postulates. Lorentz mathematically explained further the transformation which may replace the Gaussian transformation to give results in agreement with Michelson-Morley experiment. Consider two inertial frames S and S dash as shown in the figure. The system S dash is moving with a velocity v with respect to S frame in the positive x direction. Let us suppose that the axis of two coordinate systems coincide at t is equal to t dash is equal to 0. Let the pulse of light is generated at t is equal to 0 at the origin which grows in the space. Now consider the situation when the pulse reaches at point P. Let x comma y comma z comma t and x dash y dash z dash t dash be the position and time coordinates of P measured by the observers O and O dash in frames S and S dash respectively. When the pulse is observed from S, then we have velocity of light is equal to distance by time. So c is equal to root over x square plus y square plus z square by t. So we can write like this, x square plus y square plus z square minus c square t square is equal to 0. That is equation 1. When the pulse is observed from S dash, then we have x dash square plus y dash square plus z dash square minus c square t dash square is equal to 0. Why? Because here the light velocity is the same in both the frames. Next one, y is equal to y dash and z is equal to z dash, that is equation 3. From equation 1 and using in equation 3 we get x square minus c square t square is equal to x dash square minus c square t1 square, that is equation 4. The transformation between x and x dash can be represented by the simple relation. So that is x dash is equal to some constant k into x minus vt, that is equation 5, where k being independent of x and t. If we suppose that the system S is moving relative to S dash with the velocity minus v along positive x direction, so x is equal to constant k into x dash plus vt dash, that is equation 6. Substituting the values of x dash from equation 5 in equation 6, we have x is equal to k into x minus vt plus vt dash. After solving this equation, so t dash is equal to some constant k into t minus x by v into 1 minus 1 by k square, that is equation 7. Substituting the values of x dash from equation 5 and t dash from equation 7, so in equation 4 we get, so x square minus c square t square minus k square into x square minus 2x vt plus v square t square plus c square k square into t square plus x square by v square into 1 minus 1 by k square whole square minus 2xt by v into 1 minus 1 by k square is equal to 0. That is equation 8. This is an identity and hence the coefficients of various powers of x and t must be vanished separately. Equating the coefficients of t square to 0, we get minus c square minus k square v square plus c square k square is equal to 0. So k square into c square minus v square is equal to c square. So k square is equal to c square by c square minus v square. So at last we get k is equal to 1 by root over 1 minus v square by c square, that is equation 10. Substituting the value of k from equation 10 in equation 5, we have the Lorentz transformation for space. X dash is equal to x minus vt by root over 1 minus v square by c square, that is equation A. Similarly, substituting the value of k in equation 7, we have the Lorentz transformation for time. So after substituting the k value in equation 7, we get the t dash value. T dash is equal to t minus xv by c square whole divided by root over 1 minus v square by c square, that is equation B. Equations A and B are called the Lorentz transformation equations. When v is far less than c, that is by Newtonian mechanics, it is obvious from equation A and equation B that x dash is equal to x minus vt and t dash is equal to t. Thus, for low values of v, Lorentz transformation approaches to Gaussian transformation. Next one, Lorentz invariance transformation. If we assume that the system S is moving with velocity minus v relative to S dash along positive direction of x, then the Lorentz transformation equations can be expressed as x is equal to x dash plus vt dash by root over 1 minus v square by c square, y is equal to y dash, z is equal to z dash, and t is equal to t dash plus x dash v by c square whole divided by root over 1 minus v square by c square, that is equation B. These are known as Lorentz invariance transformation equations. Next topic, length contraction. Consider two systems S and S dash. Let a rod be placed in S dash frame along x-axis. If x1 dash and x2 dash be the coordinates of the abscissa of the ends of the rod, then its length L dash in the system S dash is given by L dash is equal to x2 dash minus x1 dash, that is equation 1. Now the rod is placed in S frame. If x1 and x2 are the abscissa of the ends of the rod at the same time t, then the length L of the rod is given by L is equal to x2 minus x1, that is equation 2. According to Lorentz transformations, we have x2 dash is equal to x2 minus vt by root over 1 minus v square by c square. Similarly, x1 dash is equal to x1 minus vt by 1 minus v square by c square root over. Substituting the values in equation 1, we have L dash is equal to x2 minus vt by root over 1 minus v square by c square minus x1 minus vt by root over 1 minus v square by c square. L dash is equal to x2 minus x1 by root over 1 minus v square by c square. That means L dash is equal to L by root over 1 minus v square by c square. So L is equal to L dash into root over 1 minus v square by c square. Thus, the length of the rod moving with velocity v relative to the observer is contracted by a factor root over 1 minus v square by c square in the direction of motion. This is known as Lorentz-Fréjol contraction. Special cases: when v is very small compared to c, then v square by c square will be negligible in comparison to unity, therefore L is equal to L dash. Second case, when v is equal to c or greater than c, v square by c square will be equal to unity or greater than unity, therefore L is equal to 0 or imaginary. Third case, when v is comparable to c, root over 1 minus v square by c square will be less than unity, therefore L is less than L dash. Next one, time dilation. Consider two systems S and S dash. Let S dash frame be moving with velocity v with respect to S frame in positive x direction. Let a clock is situated in a system S at a position x and gives signals at intervals delta t, that is delta t is equal to t2 minus t1. If this interval is observed by an observer in S dash frame, then the interval delta t dash is recorded by him is given by delta t dash is equal to t2 dash minus t1 dash. From Lorentz transformation equations, we have t1 dash is equal to t1 minus xv by c square whole divided by root over 1 minus v square by c square. So t2 dash is equal to t2 minus xv by c square whole divided by root over 1 minus v square by c square. Substituting the values of t1 dash and t2 dash from equations 3 and 4, in equation 2 we get delta t dash is equal to t2 dash minus t1 dash. Substituting a t1 dash and t2 values here. After that we are getting the equation delta t dash is equal to t2 minus t1 by root over 1 minus v square by c square. t2 minus t1 means delta t. This equation shows that delta t dash is greater than delta t. That means the time interval in the system S dash is greater than the time interval in the system S. Cases. Case 1. When v is very small compared to c, the factor v square by c square will be negligibly small compared to unity. Hence, delta t dash is equal to delta t. Second case, when v is comparable to c, root over 1 minus v square by c square will be less than unity. In this case, delta t dash is greater than delta t. Case 3. When v is equal to c or greater than c, v square by c square will be greater than unity. So that delta t dash is equal to imaginary. Concept of simultaneity. This means two events which appears to take place simultaneously to an observer. Consider two time bombs explode at the same time t naught to an observer on ground. Later, the two bombs are at different places x1 and x2. Now consider in this situation a pilot of a spaceship moving with velocity v relative to the ground. For him, the explosion at x1 occurs at t1 dash is equal to t naught minus x1 v by c square whole divided by root over 1 minus v square by c square. That is equation 1. The explosion at x2, that is t2 dash, is equal to t naught minus x2 v by c square whole divided by root over 1 minus v square by c square. That is equation 2. The time interval is given by delta t dash is equal to t2 dash minus t1 dash. So delta t dash is equal to, substituting the t2 dash minus t1 dash values. After that we are getting x1 minus x2 into v square by c square whole divided by root over 1 minus v square by c square. That is equation 3. Thus, the two events which occur simultaneously to an observer are separated to another observer. So, we conclude that there is no such thing as absolute time, which is different for different observers. In this way, time is relative. This is different for observers in relative motion. Next topic is addition of velocities. Consider the velocities in two reference frames S and S dash. S dash is moving with a velocity v relative to system S along positive x direction. Let us express the velocity of a body in them. Suppose the body moves a distance dx in time dt in the system S and through a distance dx dash in time dt dash in system S dash. Then dx by dt is equal to u, dx dash by dt dash is equal to u dash. That is equation 1. From Lorentz transformation equations, we know that x is equal to k into x dash plus vt dash, that is equation 2. T is equal to k into t dash plus vx dash by c square, that is equation 3. Differentiating equation 2 and 3, we get dx is equal to k into dx dash plus v dt dash. Next one, dt is equal to k into dt dash plus v dx dash by c square. Dividing equation 4 by equation 5, dx by dt is equal to k into dx dash plus vt dash by k into dt dash plus vx dash by c square. After solving, we get u is equal to u dash plus v by 1 plus u dash v by c square. This equation represents the relativistic law of addition of velocities, whereas in classical mechanics it is simply u is equal to u dash plus v. Special cases. First one, when u dash and v are smaller as compared to c, can be neglected in comparison to unity. Therefore, u is equal to u dash plus v, which is represents classical formula. Second case, when u or u dash is equal to c, that is, if no object moves with velocity c with respect to each other, then their relative velocity is always c, whatever may be the velocity of the others. So that is u is equal to c. Third case, u dash is equal to c, that is equal to v, then it represents u is equal to c. This shows that the addition of velocities of light to the velocity of light merely reproduces the velocity of the light. Next topic, variation of mass with velocities. According to Newtonian mechanics, the mass of the body do not change with velocity, that is independent of velocity. But according to Einstein, the mass of the body in motion is different from the mass of the body at rest. Consider the two systems of coordinates s and s dash moving with velocity v. In order to consider the variation of mass with velocity, a collision of two bodies in system S dash and view it from the system S. Let the two bodies of equal masses m1 and m2 be traveling with velocities u dash and minus u dash parallel to x-axis in the system S dash. Suppose the two bodies collide and after collision combine into a one body. So, according to conservation of mass, the mass of the combined bodies after collision is equal to m1 plus m2, as two bodies were moving with the same velocity in opposite directions. Hence, after collision, they are at rest in system S dash. Using the law of addition of velocities, the velocities u1 and u2 in system S corresponding to u dash and minus u dash in system S dash are given by u1 is equal to u dash plus v by 1 plus u dash v by c square, and u2 is equal to minus u dash plus v by 1 minus u dash v by c square, that is equation 1. Further, let the mass of the body traveling with velocity u1 and m1 and that of the body moving with velocity u2 and m2. Applying the principle of conservation of momentum, we know that m1 u1 plus m2 u2 is equal to m1 plus m2 into v, that is equation 2. Because after collision the two bodies are coalesced into one and moving with the velocity v, as s dash is moving with v with respect to s. Substituting the values of u1 and u2 in equation 2, we get m1 u dash plus v by 1 plus u dash v by c square plus m2 minus u dash plus v by 1 minus u dash v by c square, that is equal to m1 plus m2 into v. After solving the equation, we get m1 by m2 is equal to 1 plus u dash v by c square whole divided by 1 minus u dash v by c square. m1 by m2 is equal to 1 plus u dash v by c square whole divided by 1 minus u dash v by c square, that is equation 3. From equation 1, we know that u1 square is equal to u dash plus v by 1 plus u dash v by c square. After solving equation 1, we get 1 plus u dash v by c square is equal to 1 minus u1 u dash square by c square into 1 minus v square by c square whole divided by 1 minus u1 square by c square whole to the power of 1 by 2, that is equation 4. Similarly, 1 minus u dash v by c square is equal to 1 minus u1 u dash square by c square into 1 minus v square by c square whole divided by 1 minus u2 square by c square whole to the power of 1 by 2, that is equation 5. Substituting the equation 4 and 5 values in equation 3, we get m1 by m2 is equal to 1 minus u2 square by c square whole to the power of 1 by 2 whole divided by 1 minus u1 square by c square whole to the power of 1 by 2, that is equation 6. Let the body of the mass m2 be moving with zero velocity in system S before collision, that is u2 is equal to 0, then m1 by m2 is equal to 1 by 1 minus u1 square by c square. In commonly used notation, m1 is equal to m, m2 is equal to m naught, and u1 is equal to v. We can write the above equation as m by m naught is equal to 1 by root over 1 minus v square by c square, that is equal to m is equal to m naught by root over 1 minus v square by c square. This is relativistic formula for the variation of mass with velocity. Here m naught is called the rest mass and m is the effective mass. So here we consider the following points. First one, when v is very small as compared to c, v square by c square will be negligible in compared to unity. Therefore m is equal to m naught. Second one, when v is compared to c, then root over 1 by 1 minus v square by c square will be less than unity, that is m is greater than m naught. Third case, when v is equal to c or greater than c, then v square by c square will be equal to or greater than unity, so m is imaginary. So this is the example for the m is imaginary. Consider an analogy with a ship which is moving in an ocean. We know that some water is always dragged along the behind the ship. As the ship moves faster, the greater is the amount of the water dragged along. The ship thus effectively behaves as if its mass is increased as its velocity increased. Next one, limiting velocity of the particle. Very energetic atomic particles like photons are capable of moving faster than velocity of light in material medium. The velocity of atomic particle inside the material medium is never faster than the velocity of the light. in free space. Next one, rest mass of photon. We know that photon travels with the velocity of light. The momentum is given by p is equal to m naught v by root over 1 minus v square by c square, where m naught is its rest mass and v is the velocity of photon. According to quantum theory of radiation, the momentum of radiation p is equal to h by lambda, where h is Planck's constant and lambda is its wavelength. H by v is equal to m naught v by root over 1 minus v square by c square. That is, m naught is equal to h by v lambda into root over 1 minus v square by c square. Since for photon v is equal to c, m naught is equal to 0, so the rest mass of the photon is 0.